Amarnath also talked about is that because these are biological products, there is highly likelihood of getting impurities which are very, very similar in molecular shape as of your biosimilar main product. So it is very important to characterize them and minimize their presence in your main product. And of course, it is the higher order structure which governs the function. So why it is important? Because this is the critical one which governs your function. And if the site of binding or interaction gets perturbed because of any reason, either it may be formulation, maybe impurity, anything, it will deteriorate your function or modulate your function. So it's very important to actually identify that. Okay, so different structures, all of you know now by after 5 or 6 presentations, different primary, secondary, tertiary structures, what they constitute and how they are all called HOS. And of course, if your product and the innovator matches very closely, you see some binding curves, which essentially means that if they are same, similar, you get fairly similar idea. Okay, so challenges increases when you have increase in the molecular size. So you have small molecule like insulins which are already in the market, you have cytokines already in the market, and then monoclonal antibodies which are also in the market. But when you start characterization of all these, they all come up with their challenges. Insulin may be small, but it comes with their own challenges. And same way monoclonal antibody is large, and of course the characterizations is also very, very challenging. Then recently people started working on fusion proteins which are even larger in terms of molecular size and also additional complexity because you have something which is attached to the monoclonal antibody, and that increases everything in terms of complexity. But of course, if you want to show that it is novel or it's say biosimilar, you have to do appropriate characterization. Now this is typical slide also. I think Amarnath also showed us something similar. You want to show that your product is similar to the innovator, then you look for all these different attributes. So our topic for today's session is higher order structure, so I will talk about some of those things. Of course, if the HOS matches to that of innovator, the biological assays also started showing the same sort of similarity. Okay, the slides talks about different types of technique which we employ in our lab, and they provide information of different content. So some of them are simpler and therefore more are in routine use. Some of them are complex, which require complexity more from the money part. Also you need an expert to get the right and appropriate information. And if you look at it, the 3 or 4 important techniques which provide you highest resolution information, which is about the local information, are HDXMS, 2D NMR, X-ray, and of course the recently evolved HDXMS with the ETD, which provides you residue specific information. Psst. What happened? Did I? Okay. Okay. Right, so of all the techniques which were present in the last slide, I picked up just 2. I just picked up 2. I don't know why, but just 2. So this is just to show the low resolution techniques and where it has a demerit. Okay. So FTIR, very commonly used in biopharma industry. We look at key features. Of course, the 2 of these amide 1 and amide 2 bands are like fingerprints which we try to see whether the innovator and our product matches very closely. So we get 2 bands. One is around 1650 centimeter inverse, another one around 1500 something. And the best part is these bands provide you information on the secondary structure. But all the algorithms which are present right now only uses amide 1 band information. So essentially, if you want to show your product as a biosimilar, you can use one single information and still talk about it. What it does, so all the algorithm, when they try to elucidate, they actually deconvolute this spectra into different secondary structural elements, and then you can provide a rough estimate of what is the secondary structure content in your protein. So if you see, it has got tons, beta sheet content, tons, all of these are different bands corresponding to this, and summation of this provides you information on the secondary structure content of your product. Okay? Same way, I have got a map 1 and then a different map 2, got innovator, biosimilar, I looked at the spectra, amide 1 bands, and they clearly tells me around 1636, which is in this range, fairly beta sheet product. And if I look at my map, it is a beta sheet. So more or less products are in the light line. Now the challenge here is, you look at this amide 1, you look at this amide 1, you move it here, overlay on the top of each other, you cannot differentiate. So both will give you same information. It is the same story what I showed in the beginning. 2 with ice creams. On the top there is something, you do not know whether they are biosimilar or not. So at the moment, yes, they match us very closely, but I cannot differentiate between the two. So I go to the next technique, and then I looked at the insulin. Again, one insulin, another insulin. The insulin has multiple analogs depending upon you want to make it a faster insulin or a slow insulin. And I took one base insulin, another one insulin analog, and I tried to see the bands. Again, the band looks great, biosimilar, and our product and the innovator looks great. But the problem is, if I overlay on the top of each other, again everything matches closely. So I cannot differentiate between the products. Yes, as a first tool of test, they provide me clear information that the folding of my product is correct. So we need something else. So this is another technique, CD, very routinely used. Actually, principle wise, you all understand that there is a optical rotation involved here. So you have alpha rotatory component and then the beta rotatory, and because all these amino acids have a chiral center, the left and the right sees the light differently. You see a difference, and that difference is what you measure. So now these are 3 different patterns which you see in the CD spectroscopy. Shankar already talked about all of them in the morning. So you essentially have 2 alpha helical peaks which represent that the molecule is alpha helical in nature, and the beta sheet content is shown typically by this. So now, one of the beauty about CD is when you start looking at your protein, especially at the early stage of the program, is you want to see whether your protein is well folded or not. So you run CD, and it quickly tells you, because going to NMR or going to any other high resolution technique, it's not always very easy and not always very amenable. So you run CD, you look at the spectral profile, and you can easily tell whether the protein is well folded or not. Okay, so knowing that, again I put map 1, map 2 inside the CD spectrophotometer, and then what I see, nice overlap between innovator and biosimilar, nice overlap between innovator and biosimilar. Great, I'm happy, because as a rule of thumb and the first test, I am fine, my product is actually biosimilar. But again, if I overlay these 2 on the top of each other, they cannot differentiate each other. So they are true that molecules are coming in the right shape, but whether they are same or different, I still do not know. I took the insulin same way, overlaid on the top of each other. If I want to overlay on the top of each other, both insulin and insulin log will actually overlay on the top of each other. So they cannot differentiate molecules. Yes, they will tell you molecule has some helical content, molecule has a helical content, and if you look at the X-ray structure, you also see that the helical content is there. Okay. So yes, these tools are great, provide information on low resolution. So, do we miss something? Yes. So what we have right now, what we have is this kind of information, an envelope, which is actually a global information. But what is inside, I don't know. So my brother is actually, my cousin is a cartoonist, so I requested him, can you make Tintin? So actually he did not make Tintin, he made a biosimilar of Tintin. He doesn't look Tintin, but something nice he made. And I liked it on the first go, because when I looked at this conformation here, I see a difference. And that difference actually led to whether you can hold your book or not. And this is very important. It is the key region of your product. If that is not in the right conformation, you are going to miss the right structure function characteristics. So what we need is information from low resolution towards the high resolution, and that is the key of my talk actually. So again, I go back to the same slide. The key techniques essentially are NMR and probably the STXMS. Why I have not included X-ray? Because X-ray, first of all, would work great probably for smaller proteins. When you go towards maps, because of a lot of flexible regions, it's not always amenable for crystallography. Yes, you can fragment them, pepsin digestion, you get Fab and FC fragment, probably you can get beautiful structure, but it's not something which you want to run in a biosimilar industry on a regular basis because of the cost reasons. And see, one of the motive of making a biosimilar is the cheap cost. But if you start involving hundreds of tests which are very expensive, it will all add to the cost, and this is what we don't want. So we have to choose techniques which can provide you good information at a reasonable cost so that I can provide drug in the market at a low cost. Okay, so same slide what Ashutosh showed. So we actually, that was a trouble for me also. Shankar was there, Ashutosh was there, Amarnath was there, and I was there, all NMR spectroscopies or crystallographers access. What to present? Everybody will talk before me, and I need to find out something I should talk. So I said, okay, fine, I'll talk about something. Anyway, Ashutosh has covered these things, that NMR actually looks at some of the nucleus, proton 13C and 15, and typically in a protein. So I am only talking about this. Yes, you can do 19F, 31P, all those other fancy things. But in a protein, you talk about 1H, 13C, 15N, and this is a dipeptide. So basically some of the residues I just showed, this you cannot see because this exchanges, this also exchanges, you don't see. Actually, you can see, but they are broad lines. Now, the best part about NMR is that over the years people learned the pattern of these chemical shifts and also the regions where individual atoms falls if I have a regular structure. So for example, amide protons will always come in this region. Side chain or actually methyls would always come in this region. And that is why when Ashutosh was explaining that you can design your experiment essentially to pick regions of your product. And that's what is shown here. Okay? So in a 2D NMR, you actually resolve some of your problems. So you see some of these are, say, there are peaks which are overlapping. Now this is a small protein of which spectra still looks great, but if I go to a larger protein, you would see a very large line broadened spectra which doesn't probably provide you great information. Now 2D NMR resolves that. So now what you see is essentially nice well resolved peaks and so many probes, and each of this NH correspond to one peak. So you have information of all the amino acids of your protein except the prolines. Protein doesn't have NH. So you have still lots of information in one spectrum. And that is why if you see a difference in either of the amino acid, you will be able to notice that. And that is why you want to go towards a higher resolution technique so that you can get that information. Okay, so we go to the next slide. Now, he also mentioned that the technique as such is extremely insensitive. Still, it has got a lot of advantages. Now, just as a rule of thumb, you all remember from your spectroscopy learning days that the ground state, you have spins, you excite them, they go to the excited state and then come back, and then you record and measure the spectrum. Now, larger the gap between the two, the larger or the sensitive is the method. So unfortunately, NMR has such a small difference between the two states. And because the difference is too small, your sensitivity also goes down. Now what is interesting is that in the same spectrometer or a magnet, proton has the highest sensitivity, carbon has second, and 15N is even lower. On the top, carbon is only 1.1% naturally present, and 15N is 0.037%. So all that fancy 2D wonderful experiment with 15N NMR which I showed doesn't work on a regular basis in biosimilar industry. So you have to design new methods which can provide you good information without doing the labeling, because labeling is something which you cannot do on a regular basis. So this is what Ashutosh talked about, that we go towards the methyl NMR, because methyl NMR gives you 3 times the signal, and because of the region of the CH3 he talked about, fan and all, it gives you very sharp signals. And they are very distinct, as I showed in one of the beginning slides, that they are very distinctly present in the very early part of the spectrum. Okay, now you look at the structure. The X-ray structure clearly shows a difference between the two residues here. So one is human insulin, which is a basal insulin, and the other one is insulin Lispro, which is a fast-acting insulin. Between the two insulin, the only difference is between K and P and K, which are swapped in the other one. And by doing that, so insulin has a tendency to form hexamers. And it is always in the equilibrium between monomer, dimer and hexamer, but it is the only monomer which is clinically active. So if your product is more towards hexamer, it will slowly release. But if it is more towards monomer, your product is fast acting. Now Lispro, by doing 2 amino acid swapping, you can make it more towards monomer. So you shift your equilibrium to monomer. So it becomes fast acting insulin. Now you want to see a difference between the two. Can we prove that? And that's where, if I run all those FTIR or CD, I will not be able to differentiate. And that's difference you can easily see. That by changing the amino acid or swapping that, you can essentially see a differences in the spectra, which is very well seen here. But if I have 2 same insulins, I don't observe that. So you require techniques at a high resolution to show that my product is same. Okay. Can it be applied to product like MAB, which is a 150 kilodalton product? So our usual thought process is, for NMR, actually typical understanding is that NMR works only up to 45-50 kilodalton proteins. Yes, there are now novel techniques, advancement in technology, including NMR instruments. You probably can go up to 80 to 100 kilodalton, but again, the challenges are immense, which you cannot apply on a regular basis in a biosimilar industry. So we have to find out ways to do it. Of course, methyl NMR is a way, probably. And then what we want is more of a fingerprinting approach. So yes, when you run for a 150 kilodalton protein, and this is a NIST map, they got a very beautiful signal. What happened? They got around 210 peaks out of 221, which is 95%. So you have got 95% of probes, around 210 probes, which can account for biosimilarity of your product. It is beyond what you see on a global level from other information. The problem here is you need to have at least 0.5 millimolar of your product. And what is shown here is you need 900 megahertz of instrument. Now of course 750, 800 or 900 fairly gives you same number. With the cryoprobe technology, which is available right now in India at 3 to 4 places, you can still record this kind of spectrum. But not all MAB products in the market come with this kind of concentration. So challenge is still not gone completely. How we can resolve that? One way is, and that's probably nature's gift to us, that map essentially is connected by a good, very long flexible loop. So if can I cut that? Yes, on a regular basis we run pepsin digestion and we can actually get 2 Fab domains and 1 FC domain. But does that represent my full map? So run the spectrum and you see they are bang on the top of each other, which tells you that yes, if I chop this, make 2 fragments of this, Fab and FC, and run, and then add the 2 spectra, I'll get information which is as good as information of a full map. The advantage. Now map domain is around 50 kilodalton, Fab domain is around 50 kilodalton, and FC is around 25. So my problem of going towards 900 megahertz is immediately solved, and I can go maybe 600 megahertz, which is available in many institutions in India. So I am dividing my problems into smaller pieces, which are amenable right now in most of the biosimilar industry. Okay, and this is something recorded at Dr. Ashutosh's lab at IIT Bombay. So just wanted to show that when we ran one of the innovator and early batches of our product, a biosimilar product, see a difference. And this difference is not possible from any other low resolution technique. So once you know that, you can go back and ask your team, I think they have to rework. You have to work on your process to go towards the direction of the right product. This is something what I want to show. So now what is the alternative? Now NMR, again, the problem is higher concentration. Sometimes you may have, sometimes you may not get. Now you need some alternative way. Again, the problem for me was somebody else talking about SDXMS. So Deepak Thakur today took that chance. So he was the first speaker, he talked about SDXMS. I thought, okay, I'll change my slides to make it slightly more simple, just to show some examples. He talked about some theory, so I'll just show what we see. In SDXMS, just like NMR, you have an H, which you want to see there. Here, these are again critical because these are labile protons, they exchange with deuterium. So you have your protein product, you incubate it in D2O, and once it gets incubated, because they are labile, they exchange with D2O. Now parts which are more exposed, which are more dynamic towards the solvent, absorbs faster of this, or they just uptake of deuterium is faster. Something which is inside the core or in some secondary structure, because they form hydrogen bonding, will not exchange on the same time scale. So that's the trick what you use. So some of those will get exchanged, some of them may not, and that's what is shown and depicted in this cartoon representation. So you have D2O over the time. You take snapshots, which means you take the aliquots out of your sample at different time points. You take that, you quench the reaction at a very low pH, cool it down, and then unfold, digest, and then the analysis starts. And that's where I think his software helps you in aiding how you get the relevant information across the chain. And very essential, very important actually, because this is something which is otherwise not possible, especially when you are dealing with proteins of 150 kilodalton. Of course, yes, NMR can provide, but one of the challenge with NMR is still there, and that is the right assignment of those peaks coming out of methyls. For insulins, it is quite easy because small molecule, you can run multi-dimensional experiment, get that information. For MAPs, that is not that easy, that's not trivial. So you actually have to identify a new technique, and that's where I think SDXMS has an advantage, that you can go to residue level without labeling also. So what you can do here is, if you want to see whether the structure is binding to the right place, you go take your antigen, bind, run the same system under the same HDX conditions. You will see some portion which is in the vicinity of this in the binding partner will not get exchanged at the same rate. and you will get that information. So while I was working in AstraZeneca, we actually have done something similar, for 2 ligands binding to the main product. So what we wanted to see whether there is a change in the conformation and can be detected using SDXMS. So of course there I had also NMR assignment, but I had 1.5 years just to do that. So we did NMR assignments, and then we wanted to cross check whether everything matches closely with SDXMS. So we looked at it, and the information content was just exactly same what we saw in NMR and what we saw in SDXMS. But what I wanted to show here is some of the uptakes. The uptake was clearly distinct for the 2 different ligands. You clearly see the red and between blue, and at times they were also very similar. And when you plot those differences at a sequence or residue level basis, you see certain regions which clearly show marked difference between the 2. And when we solved the X-ray structure, we did see that the conformation of those domains were clearly distinct. So SDXMS can provide you clear information on that. Okay? So what a biosimilar people do? They do perform the SDXMS. The one is the innovator, the other one actually is a biosimilar product. You make this kind of butterfly plot of different exchange rates, and those are plotted on the sequence, and then you take the difference out of this. And that difference, if it is too minimal, then you say your product as well as the dynamic regions are just intact as like the innovator. So SDXMS and probably solution NMR are key towards going in the right direction if you want to make a right biosimilar product. And that ends my presentation with some of these key important messages that techniques can provide high and low resolution, low HOS information. These can be used up to 200 kiloton. Actually, SDXMS does not have any size limit, so you can go beyond that. And they are very, very essential for a biologic product. And this is what I wanted to tell all those from the industry as well as from academic people, that you have to use them at a very early stage if you want to guide your team in the right direction. And thank you so much for it. Please.
Wonderful talk, and I have 2 questions related to the FTIR plus the antibody with peptide digestion actually. With FTIR in the amide 1 region, it is overlapping, but it's not completely overlapping. The peaks in the amide 1 region.
Yes.
So what you go for, they are similar or not?
Yeah, that's actually a problem. So if the variability, which is also observed in day-to-day basis from, so today you run, tomorrow again, because the qualification of experiment, when you do qualification of a method, you see certain variability, and then it becomes very challenging and difficult for us to say whether it is biosimilar or not. So you understand that problem because you do it in day in, day out, and therefore I think that differences, it is hard to pick from there. But if you run either of these techniques, which are high resolution technique, that provides you clear understanding. And that's why I think these are the ways to go, but it's still far off.
Yeah. And the second question is related to the antibody with papain digestion. So most of the antibodies, I think the Fab domain and FC domains are mostly conserved actually, the secondary structure if you take part. And the conformations of the molecule changes actually here. But when you do this papain digestion, the conformation of the molecules might change.
Absolutely.
So in the fingerprinting, you are trying to print the Fab domains and FC domains, and then you're trying to say this as biosimilar as such.
Correct.
But the papain digestion, still you do that, and then you do this fingerprinting, then it's a tricky question to say whether they are biosimilar or not. Actually,
absolutely right. I think very fair question, and that is why, see, this study is shown for a map which is standard map from the laboratory in US, and there everything matches so beautifully. So they have shown this as a technique. But if I do probably on a routine basis for my products, many of these things may or may not work. I agree. But then if I treat my product, see, if for a lot of your physicochemical techniques, you extract your product out of your formulation buffers. So you are no more in the same condition what you are trying to judge.
But we pre-validation, post-validation.
Pre-validation and
yeah.
post-validation.
Yeah.
Same way, I think for papain also, we have to establish that for our product. That is very, very true. And I understand that challenge.
That is what I'm wondering, whether the technique with papain digestion should be incorporated in the biosimilarity exercise or
Actually,
not.
if you do it same way for innovator and same way for myself, and if that matches,
The domains match definitely. I mean, if you take the antibody structures and if you go the
Correct.
structures,
correct.
the domain.
You can take on.
Thanks.
It's a small memento from our side. Thank you so much.